Okay, in this chapter, we're going to go into solar energy fundamentals. This chapter is a prelude to the following three chapters, which will deal with different aspects of solar power. So, those would be passive solar, which uses the sun in a passive way to supplement heating and, in a way, cooling of a building. And then you go into active solar, which is the um, using the sun to heat, basically to heat water. It's active because there's a pump, so there's an actually active part of the system, so it's not completely passive. But the energy absorption into the water, in a way, is could be considered passive, although the water is usually being moved by a mechanical pump. And then, of course, the third of the three topics that we'll cover in solar is photovoltaics, which is the direct conversion of sunlight into electricity. But before we get there, this chapter we're going to focus mainly on some solar fundamentals that again build knowledge for the following three chapters. So let's go ahead and just start with radiation heat transfer. So this will be a little bit of a review of the heat transfer that you had in class. So reading from the slide here, from a solar energy standpoint, two areas of interest are the characteristics of energy from the sun and the response of a surface to that energy. So the starting point is to consider the characteristics of radiation heat transfer. So when we're dealing with incoming sunlight, the energy possessed by the incoming sunlight can kind of be categorized according to its wavelength, right? So there are many different regimes according to wavelength coming in from the sun. You have gamma rays, X-rays, ultraviolet, you have thermal radiation, infrared, and microwave. All of those can be split according to a specific range of wavelength. Let's go ahead and start all of this with considering the characteristics of a black body. So a black body is basically just any body that absorbs all incident radiation, regardless of wavelength and regardless of direction. So for a prescribed temperature and wavelength, no surface can emit more energy than a black body. So the black body is what we would call a diffuse emitter, which is basically another word for that it is independent of direction. So the spectral emissive power density, right, the amount of spectral emissive power is expressed in the units of and interpreted as the emissive power per unit area per wavelength. So this is the equation that would describe that. So the total emissive power of a black body is the integral of the black body spectral emissive power density over all wavelengths. So we're not going to go through all the math associated with it, but what happens is that black body spectral emissive power ends up being a function of the temperature to the fourth power, right? So that temperature to fourth power functional dependence of the black body emissive power is one of the strongest fundamental dependencies in physics and emphasizes the importance of temperature in thermal radiation. So here's an example of something. Here we have the sun represented in terms of the energy that the sun emits as a function of wavelength. So here on the y-axis, we have spectral emissive power. Here on the x-axis, we have wavelength in microns. And then each of these lines represents the functional change in the spectral emissive power as a function of wavelength for different temperatures of a black body. So the surface of the sun can be represented as a body at 5800 Kelvin. And as you can see, the emissive power has a certain functional increase and then decrease as a function of increasing wavelength. Here's another way of looking at it a little bit close up. Again, you can see that as wavelength increases, you have an initial increase in power density and then a gradual decrease over increasing wavelengths. So what we're going to try to get into now is if we look at this graph, right, we look at the spread, the range of wavelengths here, as we'll say that basically integrating all that, right, integrating this curve over the whole range of wavelengths would yield 100% of the total emissive power possessed in a black body at a certain temperature. What we want to do is I'm going to go ahead and introduce a method to quantify the percentage of power possessed within a smaller wavelength range, right? So let's say I give you a wavelength range from 1 to 2, right? So range from x1 to x2. And I say within that wavelength, what's the percentage of total emissive power, right? Let's say between this wavelength and that wavelength, right? In this area here, what percentage of the total emissive power across all the wavelengths does that small range possess? And there's basically a function that can be integrated to get that, right? So again, this equation, this whole equation represents the fraction of thermal energy in the wavelength from some 0 to some wavelength value for a certain black body temperature. Right, so we're not going to actually integrate that. I have this in tables, but what we're going to try to do is just quantify that. If I have wavelengths from 0 to some value of wavelength for a specific temperature of a black body, what percentage of the thermal energy does that range possess? And this is actually in your books. So these basically what you would do is you would go ahead and for the specific temperature, you would multiply that temperature by the wavelength. So you get a value of lambda T. That lambda T would be in the units of micrometers Kelvin. And you would find that value on this chart, right? The value that you calculate, let's say it's 3,400. And then you would get a value on the second column of this chart, which would represent the fractional percentage, right? So basically, if I went ahead and you calculated lambda T to be 3,400, you would say, well, the amount of thermal energy, the fraction of thermal energy between a wavelength of 0 to that value lambda at that temperature T would be, in this case, 36.16%. Okay, just to make sure this is clear, let's go ahead and do an example. All right, so the example problem reads, for a black body at 5,800 Kelvin, what is the percentage of energy contained in the visible part of the spectrum? Right, the visible part of the spectrum is indicated to be between 0.4 and 0.7 micrometers. Then it says contrast this with the percentage of energy contained in the visible spectrum for a black body at 300 Kelvin. So let's do that. Let's first go ahead and we're going to do this for a temperature of 5,800 Kelvin. And what we're trying to find is the fraction of energy between 0.7 micrometers at that temperature, right, 1500 K, and lambda 1, which is 0.4 micrometers. So to find that, you would basically set that equal to the range between 0 and lambda 2 minus the range between 0 and lambda 1. Remember, this chart here only gives you the fractional power between a value of 0 micrometers for the wavelength up to some value lambda that you define for some temperature T that you define. So if you're trying to find it between a range of two specific value wavelengths, you have to split the math to look from the range from 0 to the higher wavelength and subtract from that the fraction between 0 and the lower range temperature, right? So I'm going to go ahead And let's calculate lambda 1T. So lambda 1 is 0.4 micrometers, and the temperature is 5800 K. So again, that would equal 2320, I believe. And that's micrometers Kelvin. And then lambda 2T, again, which is 0.7. Then you multiply that by the temperature. That is 4060 micrometers Kelvin. If you go back to the chart, 2320 would land you somewhere between a value of 0.1008 and 0.1402. So if you interpolate, you would get that the fraction of energy. In that case, the thermal energy would be about 12%. And for 4060, you would be somewhere between a value here of 0.48 and 0.5159. Again, if you interpolate there, you would get a value of 0.491. And so 0.4913, sorry. So if you go ahead and do the math, you would take 0.4913 and subtract out 0.1244, and you would get that you have 37% of the energy contained in the visible, 37% of the energy is contained in the visible particle spectrum for a black body at 5800 Kelvin. Now, the problems ask you to take that and compare it to a black body at 3000 Kelvin. And this will help sort of illustrate the fourth order effect, right, that temperature has on energy. So again, you want to try to find the fractional energy between 0 and lambda 2 and subtract from that between 0 and lambda 1. So go ahead and do that. Lambda 1 times temperature will be, again, 0.4 times the temperature, which is 3000 Kelvin. That gives you a lambda T of 1200, and lambda 2T would be 0.7 times 3000, which gives you about 2100. Again, that's micrometer Kelvin. You go to the chart and interpolate as best you can. You can find that that in this case, fractional energy would be 0.0021 or 0.2% for lambda 1T, and for lambda 2, it would be 0.0838. So if you do the math, 0.0838 minus 0.0021 gives you 0.082 or 8.2%. So you can see that at 5800 K, the visible spectrum contains 37% of the energy, but at 3000 Kelvin, it contains a little over 8% of the visible spectrum contains 8% of the energy. So you can see that doubling the temperature, right, between 3000 and 1500, 1500 is nearly double 3000. You can see that the percentage of energy available increases more than a factor of 4. Well, yeah, it increases more than a factor of 4 just for an increase of double the temperature. So you can kind of see that effect of how much temperature has on emissive power. Again, here it is. The visible spectrum just happens to be where, if you look back at this power spectral density versus wavelength, you can see that this peak is encompassed within that visible spectrum. So going back to look a little bit more specifics at the sun, we know that the sun is located far distance, 1.5 times 10 to the 11 meters from the Earth. And then it also has a diameter of about 1.4 times 10 to the 9 meters. So the solar constant is defined as the flux of solar energy incident on the surface oriented normal to the sun's rays, has a mean value of about 1353 watts per square meter. However, the solar constant is the flux incident at the outer edge of the atmosphere. So for Earth applications, terrestrial applications, what is important is the solar flux incident on the surface of the Earth after the sun's rays have passed through the atmosphere. So this figure here in this table, in this slide, provides just sort of illustrates a quantitative assessment of the solar flux. So you can basically see that the solar flux is significantly affected by the presence of various gases within the atmosphere. So so you can see here in a wavelength in the ultraviolet regime, which is basically within the 2 micrometer to 0.2 to 0.4 micrometer range, ozone is responsible for the absorption and results in virtually no solar flux reaching the surface for any wavelength less than 0.3 micrometers. But part of the concern about the depletion of the ozone layer is that without the ozone, much more of the thermal radiation in the ultraviolet regime would reach the Earth with long-term negative effects. Okay, so when the sun's rays pass through the atmosphere, what happens then? Well, this part is going to be a little bit of a review of things that I also cover. Well, I guess it wouldn't be a review if you haven't taken HVAC, but this is a similar thing that we cover in HVAC because we look at thermal loads in buildings. For example, thermal loads in buildings, obviously the sun, the orientation of the sun has a huge effect on the amount of load a building absorbs because it has an effect on the incident solar radiation on the surface of a building. So I'm just going to actually end this video at this point, and then we'll go ahead and pick up on this in the next video.